Let's take another look at approximating definite integrals. Let's suppose that we have a function and we don't have a continuous function where we could use our fancy tools on it. We're just going to be able to approximate. The idea that we talked about yesterday, it goes back to the core idea. We're trying to find an area, and area is length times width. Length times width is the only one that we need for area because now we have calculus. So we want to look at this in terms of the graph and in terms of a table of values. Now, we're going to try to find the area under whatever this curve, whatever it may look like, using these 5 points. And so what we're doing is dividing the area into 4 rectangles. And so for each of these rectangles, I'm going to use a value for the function at either at one endpoint or the other. I'm either going to use the highest value of the function or the lowest value of the function. So here are the 4 rectangles that we're going to make, at least the verticals. That one's going to be really short. So I'm going to create an overestimate by using the highest value from each rectangle. To connect this to what we had before, these are going to be my xi. So this would be like x0. Here, that would be 0. x1 is equal to the 4. x2 is 8. x3 is 12. And x4 is 16. So in the first rectangle, let's start with an overestimate. So let's make an overestimate using rectangles. I'm going to make an overestimate using 4 rectangles. And we're going to scroll a little bit. Okay. Let's make an overestimate using 4 rectangles. Now in this first rectangle, I have my width is going to be 4. So my width is going to be 4. Nope, now I got to scroll back down. So the width of each rectangle is going to be 4. So that's the width. Now I need to get the length. That's going to depend on what value we pick. So I'm going to use the first length is going to be this 100. So I'm going to use 100 times my width of 4. And that's my first rectangle. That would represent this rectangle here. Then I'm just going to add, because integration is just an addition problem. And then my next rectangle, I'm going to use, so between 4 and 8, I can use 90 or 70, and I'm going to use 90 because I'm going for an overestimate. So I'm going to use 90 times the width of 4. And then my next rectangle. I can either use 70 or I can use 40. And I'm going for an overestimate, so I'm going to use the largest value that we saw. So I'm going to say 70 times the width, which is 4. And finally, for the fourth rectangle, I can use 12 or I can use 0. And I'm going to go in for an overestimate, so I'm going to use the 12. So
Isn't it 40?
Oh, sorry, 40. I can use 40 or I can use 0. And I'm going for an overestimate, so I'm going to use a 40. Well done, you found my carefully planned mistake. 10 points. Negative 100 points for everybody else. Just kidding, that's not how it works. And then we just add all these up. So I have 4 times 100, 90, 70, 40. So 1,200. So we know the area under whatever this curve looks like. We know that the area under this curve is at most 1,200. Now, we could construct a scenario where between 4 and 8, it goes way up here and then drops back down. And then it does that between each one of these. If that's the case, then someone is cheating. If they're like, oh no, it's actually 2,000 because it's big giant parabolas in between each of these points, then that person didn't give you enough information. And they're just cheating. So you're like, oh, okay, fine, you win. That's the dungeon master when the players corner him and he can't figure out what to do. Any questions on the overestimates? And you can see the area is being approximated by these 4 rectangles with the pink on top.
So just to clarify terminologies, overestimates right Riemann sum and then left Riemann sum, or I guess it depends on what way you're looking at the graph?
It depends on the direction that the function is going. In this case, the overestimate was using the left endpoints. This is a left Riemann sum.
Got it. Okay, thank you.
And that's since the function is decreasing. So now we'll switch it over to the right and find the right sum, not the correct sum, the right side. And that is going to give us an underestimate since f of x is decreasing. So now in each of these 4 rectangles, I'm going to use the left endpoint of the interval to evaluate the function there. So let's do a underestimate using 4 rectangles. Oops. I should know better than to make the delta x and the n the same number, but and it has to be anything other than 4. And then what did I pull? 4. If you had a professional teacher, that kind of thing wouldn't happen, but you're stuck with me, so there it is. Now I'm going to take this first rectangle, and instead of using the 100, I'm going to drop down to the 90. I'm going to say, well, this is the lowest value that I see on this interval, and I'm going for an underestimate. So I'm going to say this is the value. I'm going to make the thing constant. And so that is going to be the height of the function. So I'm going to use 90 times 4. And then I'm going to have, still looking for 4 rectangles. In the second rectangle, I'm going to use the lowest value of the function that I see on the second rectangle, and that's going to be a 70, and multiply that by 4. These are all going to be multiplied by the width of 4. In the third rectangle, I have 70 and 40, so I'm going to use the lower value. I'm going to use 40, the one on the right. And in the fourth rectangle, it's going to be a very flat rectangle because I'm going to use a height of 0. So flat rectangle. Might refer to that as a degenerate rectangle. And then we just have to add all these up. That's going to smear things. So we really just have to get rid of the 100. And there's our total, 800. And here we're doing a right sum because that's going to be an underestimate because the function is decreasing. But there are 4 areas that we're going for. Oh, I don't want to draw it in there because I'm about to draw in there. So in both of these cases, where the base assumption is that the function is constant on each rectangle or each subinterval. So these assume that the function is constant on each subinterval.
Are you going to do trapezoids too?
Yep.
Okay.
So these approximations assume f of x is constant on each subinterval. When we find the average of these two, that's the same as assuming that the function is linear on each subinterval. And instead of calculating areas of rectangles, we're calculating areas of trapezoids. So if we assume f of x is linear on each subinterval, connect the dots style, so if we just connect the dots with a line, that's assuming that f of x is linear on each subinterval, then 2 things happen. First of all, we can just find the average of the left and right approximations. Second, we're assuming that things are, we're calculating the areas of trapezoids. So here we have the left sum, and this is the right sum. Since f of x is decreasing. So when we assume that f of x is linear on each subinterval, 2 things happen. The areas that we're calculating are trapezoids, and we can just find the average of the left and right sum. We're finding the average of the left and right sum. We're also calculating the areas as trapezoids. And the formula for the area of a trapezoid is the average of the bases times the height. So the base assumption that we want to make is that we're going to make everything flat. We want to use length times width. That requires the length to be constant. So we're going to assume that the function is constant on each of the intervals. If we go, that's degree 0. Degree 1, we're going to assume everything is linear by just connecting the dots. This means that we're going to calculate the areas as trapezoids, and we can do this by finding the average of the left and right sums. Let's go back to the picture and draw what this is going to look like. And then we'll have to switch pages because I ran out of space. Then let's switch pages and actually write down this calculation to see that they're the same. So on the picture, what we're doing is we're just connecting the left and the right endpoints with a line. We're saying the function is just linear. But I have all these points, and I'm just going to connect the dots style. So connect the 90 to the 70. And we're just drawing all these trapezoids. And then this last one comes out to be a triangle because one of the bases is 0. But we can connect the function with lines. So we get trapezoids if we assume that the function is linear on each subinterval. So this first trapezoid has one base of 100, another base of 90, and a height of 4. So now let's find a trapezoidal estimate using 4 trapezoids. And I put my hand right on. All right, so let's flip the page. And we're going to find an approximation using 4 trapezoids. Still 4 of them. So now we're going to do an approximation using 4 trapezoids. To do this, we do the average of the 2 bases. So that first rectangle had a 100 and a 90. So I want to find the average of those. So I find the average of the 100 and the 90. I don't need to do that. And I multiply that by the height, which is still 4. Then the next trapezoid had a height of a 90, and then the next height was a 70. So I find the average of the 2 bases. And that still gets multiplied by 4. That's the height. The next trapezoid had bases of 70 and 40. And that gets multiplied by the height of 4. And the fourth trapezoid had heights of 40 and 0. And that also got multiplied by 4. And we can also notice that this last one is just a 1/2 base times height, since that one of the bases of the trapezoid was 0, and that made the trapezoid just look like a triangle. So if we add all this up, we can see that we get 1,000. And it's just 4 trapezoids where we have the average of the 2 bases multiplied by the height 4 times. Any questions?
Isn't this just the same thing where the left and the right numbers you multiply once and then everything in the middle you times it by 2 and then times everything by 4, right? I don't know if there's a rule. That's a specific rule.
That is the trapezoidal rule. If we didn't have the left and right approximations already, that's the that's the trapezoidal rule right from the start. Notice the numbers that are showing up here. Remember the numbers that we had in the beginning. We had 100, a 90, a 70, a 40, and a 0. So we had those 5 numbers. In the trapezoidal rule, The ones on the end, the 100 and the 0, only get used once. The numbers in the middle all get used twice, 90, 90, 70, 70, 40, 40. The numbers on the end, the values on the end, get used once. The values in the middle get used twice.
Just out of curiosity, though, does this work? These numbers worked out nicely so that the average of the two areas is also the same as the average of all of the trapezoids. That's not always going to be the case, is it?
The average of the left and right approximations will always give you the trapezoidal rule, just by construction.
Okay, great.
I made the numbers work out so that I could do the average fast in my head because I'm not very good at arithmetic.
Sorry,
So the values on the end get used once. That's the 100 and the 0. Notice that the values in the middle get used twice.
Sorry, could you write what Heather was talking about, the trapezoidal rule, or is that what you have up?
That's what I'm going to do next.
Oh, okay, got it. Sorry, thank you.
So notice that the 90, the 70, and the 40 all get used twice. So also notice that there's a common factor of 4, and there's a common factor of 1/2. Okay, so we have a common factor of 4. And we also have a common factor of 1/2. If we just overzealously multiply everything out on our calculators right away, we start missing out on things like this. I know that this means that there's a common factor of 2, but I don't want to break it. I don't want to combine those two things yet. So I want to factor out the common factor of 4, and the common factor of 1/2. And then I'm going to write down the values on the end getting used once. That's the 100 gets used once. But the values in the middle get used twice. So we have 2 copies of the 90 plus 2 I forgot to write the 2. A professional YouTuber would be able to edit this out. But unfortunately, you have me. A professional mathematician would have made the mistake in the first place, but unfortunately for y'all, you got me. So we have 2 copies of the 90, so 2 90s. Plus 2 copies of the 70. The ones in the middle get used twice. Plus 2 copies of the 40, because the ones in the middle get used twice. But only 1 copy of the 0, because the ones on the end get used once. Now, if I take this and punch it all into my calculator, it's still 1,000. And this is sometimes referred to as the trapezoidal rule. Which doesn't technically show up until chapter 7, so you guys are really advanced. Nice. In general, what's happening is we take the delta x and divide it by 2. This dividing by 2 comes from the fact that we're finding trapezoids and finding areas of trapezoids. And to find the area of a trapezoid, you average the 2 bases of the trapezoid. So there's the delta x divided by 2, and then we're adding up 1 copy of the values on the end and 2 copies of all the values in the middle. So what it would look like in general is we would say delta x over 2, and then we'd use f at x0, because remember, all we're doing is evaluating the function at a bunch of different points, plus 2 times f at x1, plus 2 times f at x2, and so on, until we get to f at xn, where we use 1 time. The ones on the end are used once. The ones in the middle get used twice. Any questions? Cool. So that's what I was on about yesterday, talking about finding areas of trapezoids. And then we could see that these things work out this way. We have one more thing to do, because I said the trapezoidal rule should be the average of the left rule and the right rule. So we should also see that this should be the average of the left and the right rules. So this should be the average of the left rule and the right rule. Let's see how that works. Notice that in each of the trapezoids, I'm finding the average of the value on the left and the value on the right. So in each set of parentheses, I've got a left and a right. Then 90 is the left, 70 is the right. Then 70 is the left and 40 is the right. Then 40 is the left and 0 is the right. So if we go back to our original colorings, the 100 is a left, then the 90 is a left, then the 70 is a left, and then the 40 is a left. And then the 90, in that first trapezoid, the 90 is the number on the right. So there's the right, the 70 is on the right, the 40 is on the right, and the 0 is on the right. So we can start pulling these things out. The 1/2 is the average. And notice I've got a 100, a 90, a 70, and a 40, just like I had in the left approximation. So I've got 1/2. Then for all the numbers that were in the left calculation, I had 100, a 90, a 70, and a 40. And those all get multiplied by 4. So this whole thing is my left approximation. Then I also have one for the right approximation that I'm going to add up. So on the right, we had a 90, a 70, a 40, and a 0. All these got added up and multiplied by 4. So this 1/2 is for the average part. This first term in the parentheses is the left approximation. And this second set of parentheses is the right approximation. So here we are, assuming that the function is linear on each subinterval. That means we could just take the average of the left and right approximations, if we have them, or we can calculate the area using trapezoids. Those things are all equivalent. Any questions? Comments? Snide remarks?
Nope, just a thank you.
Next time on Calculus 2, we'll look at the fundamental theorem of calculus. So next time I want to look at the fundamental theorem of calculus, and then take a look at the rest of the homework on chapter 5. And if you have any questions, we'll talk about those on Monday. Then we can start getting into chapter 6. Any
Sounds good.
questions? Questions? Comments? Snide remarks?
Yeah, that's all on Canvas, right?
Yeah, all these assignments are currently on Canvas. I think the chapter 6 ones don't have a due date yet because we're not ready to decide when those assignments are going to be due. Also, there is the first quiz on section 5.1. So quiz 1, the definite integral part 1 is up there. This quiz won't get graded as soon as you do it, like the homework. The homework immediately tells you right or wrong. This one, you have to wait for me to go in there and start scoring the problem. So who knows when that'll take place. We should be set for chapter 5. There might be some things that you have to check out in chapter 5 that I conveniently left off for you to struggle with over the weekend. But that's just the way things happen.
Is there a due date on the quiz?
it's
The
the
quiz is
26th.
technically due the 26th, I think. So I want you to work on that quiz this weekend. All right. Well, that's going to do it for today. That's going to do it for this week. I'll see you all next week. Everybody have a good weekend, and thanks for playing.
You too. Thanks, Professor.